scroll up here and paste it back in. And I did this, I went ahead and I put both series on the same scatter plot, but that's kind of a dumb idea for this. You can split axes. I think you guys probably already know that. But I do it on purpose just so I can copy paste and then I'm just going to delete. It's easier to do that than it is to select the rows twice.
Do you play connect the dots
once? Actually, that's a good point. I don't like how this looks with lines, so I'm going to switch it to, with dots. So.
Why can you graph on both of this?
I mean, you can. I just didn't want to. But yeah, you can put them on the same plot and then just make one of them appear on a secondary axis. Otherwise, you're not going to see conversion, right? Because the scales are too different. So you'd have to put one on a secondary axis. Okay, so temperature drops and it decreases rapidly at first, and then the decrease in temperature tails off, right? And that's again because the rate is higher initially. And conversion does, it looks the exact opposite, right? The conversion increases dramatically at first because the rate's highest at short volumes, and then it tails off as well. So just as what would happen if I made the delta H of reaction 0?
Linear?
Would it be linear? So this is what we did in the first part of class, right? This is now it's an isothermal reactor. Would we expect a linear concentration profile along the bed of the reactor? A linear conversion profile? For an isothermal reactor? No, why not? The rate's still decreasing, right? Why is the rate decreasing? For an isothermal reactor, it's decreasing because the concentration is decreasing. As the concentration of A decreases, the rate decreases. Now it's just sort of paying double duty. It's decreasing both because the concentration is decreasing, but also because the temperature is decreasing. I change this to 0, and you see that a 500-liter reactor is more than sufficient for doing this reaction, right? We essentially go to 100% conversion way back here at 200 liters if we could run this isothermally. But we still see this similar profile in conversion, that it increases dramatically at first, and then the increase tails off at the end. Of course, reaching an acid and product value. And if it were exothermic, what would we expect? So the temperature is going to increase. What's going to happen to the rate? It's harder to tell, right? Eventually, it's going to go to 0. If I'm at 100% conversion, the rate is 0. So I know that eventually the rate has to decrease. But it can go through local maxima, which you may or may not be able to see. You're not going to see it on this type of plot. So now you really can't see it on the plot because it happens too quickly. And also, this is actually a good point. So remember that these are approximations. So you see that it's breaking down, right? These are not meaningful values of conversion. Negative 1.5 is not a meaningful conversion. So we would have to decrease the step for an exothermic reaction. Yeah?
Can you put this file on Canvas?
Yeah, I'll upload it. So you guys see that you get nonsense, right? Again, it's because the step size is too large. The rate's changing too fast. There's too much changing too quickly for me to use a step size of 1 liter when I'm dealing with an exothermic reaction. When I was dealing with an endothermic reaction, everything was fine. So these are the things to look out for. You will get very obviously wrong answers if you have a step size that's too large. Okay, but that's not what the question asked. The question is asking about what happens with the concentration of a NURBS. Or as I increase theta I, what happens to these profiles? So let's go back to our equations, and first we're going to look at what changes with our equations when theta I is not equal to 0. Okay, so does anything here change? Yeah, sorry. Should have done. So does anything here change?
Yeah.
Yeah, what? Can I use CA naught there? No, what do I have to use instead?
Epsilon changes.
Okay, so when theta I was equal to 0, the concentration entering the reactor was the same as the concentration of the feed. But now that's no longer true. The concentration entering the reactor, well, we already solved for that. That was part A. That's why they asked you to solve for it. So we already have that, so we're good to go there. We know the concentration to use. What else changes in the design equation? Epsilon, right? Epsilon. So again, not only was this true, but also epsilon was equal to 1 because delta was equal to 1 and the mole fraction of A entering the reactor was 1. It was pure. So epsilon, delta, does delta change? No, right? Delta is a property of the reaction. We haven't changed the reaction. But what changes now? YA naught is no longer just equal to 1. How do we get that? It's the flow rate of A entering the reactor divided by the total flow rate entering the reactor. The flow rate of A entering the reactor is the same as the flow rate entering the system, the feed. The total flow rate is that flow rate plus the feed of inerts. And I can rewrite that in terms of theta I. And so that is all equal to epsilon because delta is equal to unit. Okay, so that's the design equation. What about the energy balance? What changes in that formula over there? We'll do the one on the right. So we get temperature is equal to T naught plus. Does the heat of the reaction change? No. Conversion doesn't change, but what changes? What should be the denominator there?
You have to add a CP of
Is that correct? No. Anybody remember their energy balance equation before we substitute things in? It's the sum of what two things?
Entropy in and entropy out.
Yeah, you're going way back though. I'm just talking about this particular term. It's the sum of theta I times the heat capacity of I. And doesn't that make sense to you? I mean, doesn't that, how much of it you have has to be in there, right? If you have 1,000,000 times more of it, it should make up a larger component. If it's not there, it shouldn't be there. So this should say, of course, there's a theta A here too, but theta A is by definition 1, right? So we don't need to write it down. It was kind of always there the whole time, right? All of these equations, I could have started this problem and just not made this assumption that theta I was equal to 0. And all you do is you just substitute in theta I is equal to 0. Okay, so that term goes away. That's what we had over there. Theta I is equal to 0. So the mole fraction of A is 1. Theta I is equal to 0, so the concentration is just this concentration. So it was always there. It was just always equal to 0. So any questions about how these equations have changed now that we have an inert flow? Okay. Everybody got that? Yeah.
Your T-naught still be coefficient now that you have that in the fraction? Wouldn't that be on both sides? CPA plus the delta odds.
So if I'm back here, if I'm here, then you can write it out as the initial temperature of the feed of the A stream plus theta times the heat capacity of air times the initial temperature of the inert stream. But luckily in this problem, those are the same. The two temperatures of the two streams are both 1100. That was in the problem statement. So I don't have to worry about T subscript I naught. It's just T naught. And that's most of the time going to be how these problems are set up. Not a guarantee, but. Okay. Oh, yeah. Yeah. Sorry. I always do that. I left out a negative sign on the